Hello friends, for our BSc program in Geography, we have a course on the elements of physical geography in which we have a block on atmosphere. Elements of weather forecasting has not been covered in detail in our print study material which we are covering in this video program. So the topic of today's discussion is observing weather and meteorological services, and for this we have in our studio Dr. L.S. Rathore, who is the Director General of India Meteorological Department, Government of India. After viewing this program, you would be able to define meteorology, understand the real functioning of IMD in terms of observing and monitoring the atmosphere, and correlate how the information generated is helpful in different sectors of economy and also disaster management. Over to you, Dr. Rathore.
Namaskar. In next 20 minutes, I shall be talking on how the weather service is being organized in this country. And since there are two components, component number one deals with because the service starts with observing weather. So how we are observing weather and how the services are being rendered, and then subsequently we'll talk about how the prediction and the prediction skills. The meteorology impacts all spheres in science, directly or indirectly, and therefore the study which is related to atmosphere, atmospheric processes and its application to various sectors of economy are very important. Next 20 minutes I shall be touching upon how we are observing weather and how we are developing various applications which are leading to the kind of service we are rendering to various sectors of economy. And before I start as to how meteorological department is doing and what it does, our first prime job is to observe weather and then produce weather and climate forecasts and warning, because these are very significant components of minimizing losses due to natural hazards. And this problem has four broad components. After you observe weather, you need to analyze to identify as to what are the kind of systems which are prevailing at that point in time in atmosphere, and then try to address as to how they are dynamically moving both in time and space and how their intensity is varying, and that's what we call as forecast. And third component is once you understand as how it is likely to behave in next time over different spatial domains, then you try to relate it to various sectors and how that weather is going to influence, and in that essence you try to understand the weather sensitivity of various activities, and finally as to how to communicate weather and advisories to the stakeholders and user at large. And the third component which the department is doing is to provide data and products, because data and products are very critical, and therefore how we record observations and how we do forecast are very critical. In the recent past, there is incremental use of meteorological information in various sectors of economy, and this has primarily come because of three aspects. Aspect number one is because in the recent past there is a significant improvement in the quality of weather forecast in different temporal ranges, and that has come through better understanding of the scientific processes and better modeling and better observing systems. But also, and equally important, is that today the user has a better capacity to consume that information And also in today's economic realm, there is essentiality for using this information to minimize the cost of various operations. And it has also been added by increased awareness and increased capacity for different users in different sectors, and also ongoing incremental costs of inputs in various processes, be it agriculture, be it industry, be it hydrology, or be it aviation, is increasing, and therefore the only way to minimize the cost is to capture the weather sensitivity and factor that information into their operations. And lastly, because of this global awareness in the climate change, which is now happening at a very rapid pace, also is added to that. As we have noticed that recently there is a significant improvement in the skill, and that has primarily come first because we have now better understood the atmospheric processes, how it is atmosphere is coupled to ocean, coupled to land, and interconnectivity between land, atmosphere and ocean. Better observing systems, better communication systems, better analytical techniques, better models, and better infrastructure for running the numerical models. Now, when it comes to observations, and observations are primarily required in the context of weather forecasting to define the initial state of atmosphere. And when I said to define the initial of a state of atmosphere, I mean that atmosphere which is enveloping the mother earth, you have to three-dimensionally simulate atmosphere at a given resolution. And for example, at this point in time, we are running global model at a horizontal grid resolution of about 23 kilometers, and slice the atmosphere into 64 vertical layers. And at each grid point of this simulated mesh, you have to assign value of meteorological parameters, that is temperature, humidity, pressure, wind speed, wind direction, and so on and so forth. And that is done through observations. There are two important characteristics which is really very important. While we take observations, it has to be very precise, very accurate. If your observations are erroneous, obviously you are not able to precisely define the initial state accurately. And also we know that observations are recorded once and used for lifetime, forever. And therefore, if you are really taking wrong observations, it has multiplicity or multiple impact for subsequent users, and these are used for various applications beside the weather forecast. So, when we are talking about observations and its role in defining the state of atmosphere, it is a very complex situation, because you have to deal with observations in a three-dimensional mode. And therefore, we have a host of observing systems which try to capture the physical characteristics of atmosphere, not alone atmosphere, but also ocean, but also land surface processes, and so on and so forth. And in order to do that, we have radars. Presently, we have 16 radars, and we are now augmenting our radar systems. We have automatic weather stations, about 675, then mini automatic weather stations we call as automatic rain gauges, then surface observatories, these are manual observatories, then aviation observatories, high wind speed observing systems, hydrometeorological observatories. Then we also have large number of non-departmental observatories which report and provide data to us. Also, it is very critical to take the vertical profiling of the atmosphere, and that is done through upper air soundings, and that is the kind of equipment we release along with balloon having a transmitter which observe and transmit the signal to the ground stations in real time mode. And we also have pilot balloon which give only wind speed and wind direction. Also, we have large number of other ancillary observing systems, be it agrometeorology, evaporation, soil moisture, dew, evapotranspiration, then ozone measurements, air quality measurements, radiation measurements, and other observing systems which are adding to the improved understanding of the atmospheric characteristics, including aerosols and other solid matter particulate and greenhouse gases. So, in order to give a glimpse of what kind of network we have, I would just run through these slides, and these are the kind of surface observations, automatic rain gauges, radars, aerodrome stations, environmental network. But these all observations are at random space, and we have a convention which is set up by the World Meteorological Organizations, that every country is supposed to record observations at specified synoptic hours, which is 3 hourly at 3 hourly interval, and communicate this data, exchange this data with entire global fraternity. Notwithstanding this, you still have large number of gaps. You do not have observations over oceans, 2/3. You do not have observation in polar regions, mountainous, deserts, poor countries who are not able to maintain these observing systems. And therefore, we rely on observations which are, or rather estimates which are taken through satellites. Satellites are basically, we have 2 types of satellite, polar orbiting and geostationary satellites, and they do not per se record temperature, humidity, wind, so and so forth, but they only record, or rather estimate, spectral properties of the body which is emitting radiation. And you have to translate these spectral signatures into meteorological elements, and in the process you also develop some error, because these are again estimates. So, let alone forecast, even to define the initial state very precisely is the biggest challenge. And at point x, when you are embarking upon point t, if you are embarking upon issuing the forecast, you have to define as to what is the quantum of error at that point in time. And the challenge is that we minimize this error, because there is a theoretical limit to predictability, and we define predictability in theoretical parlance, that if this error, when you run the model, it propagates, and in the process it doubles after some time, and beyond that point in time the forecast has no value. So, this is the theoretical limit. So, x becoming 2x happens in tropics in 4, 5, 6 days depending upon the season, but in extratropical region this doubling of error happens in a much longer time frame, 2 weeks, at times even 20 days. And therefore, we often see that the extratropical accuracy of weather prediction is better than that of tropics. So, the challenge is, through observations we have to minimize this error in defining our initial state. And for that we have a very wonderful global meteorological telecommunication system, which is a dedicated telecommunication system, because here it is very critical to save the time. Once you record the observations, instantaneously it has to be consumed, and if you lose the time in communication, because you have to take the observations, decode it, transmit it, then decode it, and then assimilate it. And when I deal with this data at any given point in time, we are dealing with every 6 hourly 20 gigabytes of information. So, this is so bulky information, you need supercomputers to process all this, and therefore, all the countries first they assimilate their data at a one nodal point, and then they share with the global fraternity, and this is the kind of network we are operating. This is the network which I am showing is only for Asia region, that is RA2 region of World Meteorological Organizations. We have 6 such regions which are operating, and this is a kind of under the compliance of World Meteorological Organization, we call as WMO information system, WIS, and India is a global data dissemination center which we have located at IMD Pune. Now, coming to applications, because weather impact every walk of life, every activity, and there is a very strong economic impact on various activities. So, these are the sectors which we are rendering service to, starting from aviation to agriculture to shipping to hydrology to transport to power to tourism to cyclone, disaster management, flood, defense, pilgrimage, mountains, fog, fisheries, and then climatology and urban development. And for each type of activity, the kind of requirement which user have is not uniform. So, therefore, you have to do lot of tailor making in address to address the requirement of a given sector. And for example, for hydrometeorological sector, we are generating broadly the parameters. First, we have to have a real time monitoring of the rainfall, prepare various types of charts, and then for reservoir management, for flood forecasting, though the domain is with Central Water Commission, but the weather forecast for rainfall forecast is provided by Meteorological Department to the Central Water Commission. So, also drought monitoring and drought forecast, though the domain lies with Agriculture Ministry, but we give the basic input. Then design storm projects for various hydraulic structures and the return period of rainfall, etc. The rainfall statistics generation, rainfall climatology, and these are kind of information which are required for various activities. Another very important activity is weather service for agriculture and for farming community, and in that process we are generating as on date district level forecast for all the districts. Forecasts are prepared for a week, next 7 days, and disseminated to various agrometeorological field units which are located with various state agricultural universities or institutes of Indian Council of Agricultural Research, who translate this weather forecast into actionable advisories as to what farmer is required to do, and that again is a very wide activity, because for rice it is something different, for mustard it is different, for it is very highly crop specific, soil specific, and again there is a dynamics of pest and disease, because pest and disease also are highly weather sensitive. For a given type of weather situations, they may die because of the weather extremity, and if the weather is very favorable to them, they grow faster, and therefore you need to also predict as to how they are going to intensify and then take the control measures. And this is then disseminated to various channels. I will also touch upon that, and this dissemination is done through all modes of communication, both TV, print media, radio, then other ICT mode including internet, and also mobile SMS service. Presently we are reaching out to 72 lakh farmers who have registered with various service providers to receive the alert and advisories which are crop specific and district specific. Also, Ministry of Agriculture has launched Kisan portal, and about 1 crore farmer are using information that, and through Kisan call centers also. So, there are various modes of, because information dissemination is a very vital component. We are generating also 20-day forecast. Based on that forecast, because farmers need to take both tactical decision and strategic decisions. Some decisions which he has to take a strategic decision, and for that he need a longer time frame, and so different types of forecasts are provided to him. And the impact which is carried out by National Center for Applied Policy Research, that we are able to, this information is able to have economic benefit of about saving 10 to 25%, and primarily coming through saving the cost of inputs, that is fertilizers, pesticides and irrigation. Then support to marine, because for ships which are operating, for fishermen who goes to the high seas, they need the weather support, we are providing that. Aviation is again one very important activity, and they need forecast current weather for that area from where they are to take off, then route forecast and destination forecast. And it is highly sensitive because it depends both on temperature and wind. because the buoyancy of the aircraft and load carrying capacity of the aircraft will depend on the temperature stratification, and therefore at times you might have noticed that there are sometimes passengers are offloaded or their luggage do not come. It is because of that. And also you have to provide the route forecast as to what is the kind of weather situations aircraft is going to encounter, and the terminal forecast, and particularly visibility is very critical in Indo-Gangetic plains of India, and we are providing that. Coming to the intercomparison of the cyclone, which is causing lot of devastation to life and property. Our skill which have improved in the recent past, it's a comparative study of the Paradip cyclone which occurred in 99 to the cyclone Pelin at the same place in 2013, and this is the comparative study as to how the science is really helping to minimize loss of life and property, tremendous saving. There is a general awareness in public at large now to consume this kind of weather information, both in terms of observations and forecast, and last year the cyclone Hudhud stand in the 9th position of top searched news events, and most of it is attributed to have an access to the weather forecast. And our website, every month about 7 lakh visitors do take weather from the IMD website, though there are multiple sources. And so this year a survey was conducted as to what are the top a dozen activities in science and technology, and weather forecast and consumption of weather information is at the top of that. So that is how the meteorology is impacting the various activities, and that was reflected in Prime Minister's speech to the Indian Science Congress this year, where he mentioned that our scientists put Mangalyaan in the Mars orbit in the first attempt, and I must congratulate Radhakrishnan team and their accurate prediction of cyclone Hudhud, which saved thousands of lives. So these are the kind of societal impact and the administrative support for the kind of activity. Now, in order to further improve, as I mentioned that most of improvement, there are 3 critical components. First, to improve the observing systems to minimize the initial error. Second is to develop the better models to improve the skill, and thirdly to have better information dissemination and application processes. And for all 3 segments we have a good roadmap in a 12th 5-year plan to improve the efficacy of service delivery processes. Thank you very much.
So friends, in this lecture we have learned about the role of IMD in measuring the initial state of atmosphere with utmost precision so as to run complex error-free models for accurate weather prediction. In the next part of this program, we would be focusing more on the prediction skills of IMD with special reference to extreme weather events like cyclones, thunderstorm, fog, heat and cold waves, etc. Thank you.